Alright, today what we're going to do is study some processes that involve this idea, this ideal gas law, PV equals nRT. And last time we discussed how the pressure times the change in the volume is really the same thing as the work, which can lead to changes in the kinetic energy represented at least in part by the temperature. And so these are the processes that we're going to go through, and there's isothermal, which just means same temperature, iso for same, thermal for temperature. And then these other ones we'll also go into some detail with. Isothermal, though, is probably the most important in terms of understanding the basic idea of these processes. And we're going to do them by using something called a PV diagram, pressure volume diagram. And these pressure volume diagrams are generally not well liked by students, but they're really just big puzzles or little puzzles, and if you treat them as such, they can actually be pretty enjoyable. And before we get into that, there's a couple things that are going to come into play, and one of the main things is the heat reservoir. And this is an idea where you just take something that's going to be really big and really hard to change the temperature of it, and you dump your excess heat, or you grab needed heat from it without really changing the temperature of the reservoir. And a lot of examples that we have of it involve water. And one of the reasons for that is because water has that really high specific heat. So even if you don't have a huge amount of water, you're able to change, or you're able to put a lot of energy into it or take a lot of energy away from it without changing the temperature that substantially. So you might have water tanks as a heat reservoir. For example, if you're trying to use more passive heating, what you might do is put water tanks around your house or slightly inside of your house and let them heat up during the day, and then you'll have these reservoirs of heat at night. Industrial complexes often use things like rivers and lakes and oceans as their heat reservoirs. So they'll dump really hot stuff into a river, and the river's temperature really doesn't change as a result of this. Now, in that immediate area, you might get a temperature change, and depending on the type of creatures living in the river, you might kill off all the little fishies. But overall, the temperature of the river doesn't change. The atmosphere, also a great source, or a great place to put excess heat, except that, we can do other things that might affect the temperature of the atmosphere. But generally, adding the heat that we add to it isn't the cause of it. The chilly depths of space is fantastic because the universe is pretty large, so if we can get stuff out into the universe at large, we can do a pretty nice job of it. And in general, fluids are better than solids because of convection. Solids can't convect very well or easily, but fluids can, and this is a very quick mechanism by which you can change where heat is located and the distribution. Alright, so isothermal. And I'm going to be showing you some diagrams of the isothermal, but just to go through the basics of it. Iso means same. And you've seen this word, or this prefix, in chemistry, in geometry, isosceles, triangle, all the same sides. And so it just means the same temperature. And an isothermal process, then, is any process in which the temperature, and thus the internal energy, if you remember, that in order to have a change in the internal energy, there must be a change in the temperature of a system is unchanged, though heat may be transferred. So the way that this works, then, is if you have your work equaling the amount of heat, then you can have an isothermal process. And I'll show you this in just one moment. The work that's done is obviously done through that volumetric expansion that we talked about in the past. And because this T is constant, if we're keeping T constant, this whole side of the equation is constant, which means this side of the equation is constant as well. That doesn't mean that the volume stays the same or that the pressure stays the same. It just means that they change proportionally to each other, so they're constant. So if you have positive work being done by the gas on something else, then the pressure will decrease as it does this positive work. So let's look at a couple of examples of this. In this example, this is just kind of the basic example that we've run through already, where we have a piston. So that's this part right here, this line right here, and maybe I'll make it a different color so that it pops out a little bit. So here is just a platform, and we're going to rest some masses on this platform, and we're going to have this gas inside of it, and the gas is bouncing around and so on. And there's going to then be a force downward from gravity, and there's going to be a force upwards from the gas. And I'll call that the force from the pressure, let's say. So we have the force from the pressure, and we have the force of gravity, and if they're equal to each other, nothing is really going to happen. But in this case, what we're going to do is we're going to set the force of the pressure to be greater than the force of gravity, at least for right now. Okay, so basically this is going to go through some expansion. And I already went through in previous lectures how this expansion is related to a change in the volume. You have a change in the displacement, there's an area through which this platform moves, and we get volume, or a change in the volume as a result of that. Now, what's going to happen here is because the gas, the pressure, is doing positive work on these objects, it's applying a force upwards, it's moving them through a distance, so X is in that same direction. We know that the gas is losing energy. Okay, and if you have questions about that, look back at some of the previous lectures on P times V. I think it's lecture 6. Lectures 5 and 6 would be most pertinent. And you'll see that when the particles collide with this platform, they're going to slow down. The platform's moving away from them, they hit it, they lose energy, they slow down. Or you could think of them as imparting some of their energy to this platform to get it to go up. In any case, they're going to come back, they're going to bounce back with less kinetic energy. And that's going to cause what you would suspect to be a temperature drop. The problem, though, is that for isothermal, we're saying, well, hold on a second. This change in the internal energy, unless we're undergoing a phase change where the temperature doesn't change, but the internal energy does. If we just have gas and it stays as a gas, which is the presumption for this entire unit, this is related to, I should say related to, the change in the temperature. And in this case, our change in temperature is 0 because we're looking at an isothermal case. Okay, so if we're looking at this isothermal case, this change in internal energy is 0, which means if the particles would be slowing down on their own, what we have to do is add in some heat. So if I rewrite this equation now, let's just say that the pressure, well, actually, let's go back for a second and do this in a very simple way first. Let's say that we do, the gas does, let's say, 20 joules of work. How much heat do we have to add? And the answer to this should be pretty obvious, 20 joules. If we're going to do 20 joules of work, to not lose any internal energy, to not have a temperature change, we have to do the same amount. We have to add in the same amount of energy that we're giving to something else. So these particles are giving 20 joules to this platform and these masses. So they need 20 joules of heat added in to compensate them. If you saw something like this, where it's the work is equal to negative 40 joules, let's say, this is the work being done by the gas, this negative means that the gas is actually having energy added. Energy added to gas. And the way that that occurs is if the platform was dropping. So these particles aren't moving fast enough, they're not bouncing hard enough against the surface to keep it in place. So what ends up happening is the surface starts to fall. And when that's happening, it's colliding, it's giving some of its energy to the particles. So in order to keep the temperature the same in this case, what you would actually have to do would be to remove heat from the system. And the way that you might do something like that is to put ice cubes. You could put some ice cubes around it, and so on. And then our heat direction wouldn't be this way, it would be that way. would be out. So we would be then removing energy from heat. So we would be heating something else up around it in order to keep the temperature of this from rising. So the compression causes temperatures to rise, the expansion causes the temperatures to drop. And what I'm going to do now is I'm going to show you maybe a more specific example with a diagram involved. Okay, so what we're looking at here then are just two numbers for the pressure and volume initially of our gas. And let's say that the initial pressure is 200 newtons per meter squared, and then we get a volume at this pressure of 2 meters cubed. Well, at some point, the pressure of the gas has increased to 400 newtons per meter squared. Now this is going to happen because the volume is decreasing. Okay, for an isothermal reaction, we have to bear in mind that PV is proportional to the change in the temperature, and there's zero change in temperature. So what that tells us is that PV, let's do PV final, volume final, is equal to the P initial, V initial. They're going to be proportional to each other. We have to keep these the same, or they equal different temperatures. Hopefully that makes sense. If we increase the pressure and increase the volume, then we have much more rapidly moving particles. There's no way that they can cover the size of the container at the same speed they were going before. So the result here is that we're going to be reducing the volume, and that means the particles don't have to go as far to collide with the surface. And that means that more collisions at the same speed, more pressure. Now what this looks like in a graph, because the graphs are actually really important for these. We'll do a P and a V. So this is our pressure, this is the volume. And what it's going to look like is if I mark my initial points here. Initially we were at, let's say, 200 and 2. So this was 200 and this was 2. And then we got up to the points 400. And what are we going to be at now? Well, these numbers have to be the same. So this is 400. That's already 400, so I know that this is going to be 1. And so we have a point here. We have a point over here. And what this is going to look like is this is a classical inverse relationship, where as one gets larger, the other one gets proportionally smaller. So it's going to look something like this. And all isotherms, or isothermal processes, will fall along a line like this. If we started off with a different temperature, what that would be like, because PV is proportional to the, this should actually be P delta V, would be proportional to the change in temperature. PV is proportional to the temperature. So if I have a larger product of P and V, I get a larger temperature. For instance, if I do P equals 400 newtons per meter squared, and V is equal to 2 meters cubed, then I'm still going to have this here. It's going to be at 400, but it's going to be over here at 2. And so then you could ask yourself, well, what will the pressure be when the volume is 1? So the pressure when the volume is 1 is just going to be 800. So it's going to be much, much higher. It's going to be all the way 600, 800. It's going to be somewhere up here. So you're going to get an isothermal reaction along this line. Conversely, we could do something where we have 200 and an initial volume of 1. So our pressure and our volume 201. And so if we have 201, we're going to have an isotherm that looks, it'll be at half of a meter cubed when it's at 400, and it'll be at 100 newtons per meter squared when it's expanded out to 2. And we get something along this line, or this curve. So this is your basic isothermal process. It's going to go in this inverse relationship, and in this direction we get lower temperatures, and in this direction we get high temps. And I'm going to continue talking about these PV diagrams and some of the nuances of them, and we'll get into some of the other processes as well.